And just to introduce some notation, let me let U1 through UR and V1 through VR be the columns of U and V respectively. We have a rank R matrix. These are the things which are uncorrelated with the standard basis vectors. That's fine. Now, just to make our life simpler, what I'm also going to do is I'm going to let UR plus 1 through UN and VR plus 1 through Vn be any completion to an orthonormal basis. Doesn't really matter how you choose UR plus 1 through UN and VR plus 1 through Vn. This is all just a thought experiment that'll allow us to define the types of objects that we need, and it doesn't matter how you do these things. Now, the crucial thing that we'll be interested in, this is going to come up again and again, is a particular space T over matrices. And let me actually define T perpendicular first, just because it's slightly easier. So it'll just be defined as the span of the UI VI transpose, where both UI and VI come from this augmentation. So this is T perp. This is a span over, this is a linear space over matrices. Does this definition make sense?
Is the UI Vj?
Yes, sorry. UI Vj. So this definition makes sense? Just a linear space over matrices. And all we're doing is you can choose any pair from this completion. So T now, you can define it, and how could we define, what? We're also going to get it that it's the span of these UI Vj transposes. What allowable values for I and j should I allow here to make it perpendicular to T perp?
Probably at least one of them should be in the
Exactly.
initial.
Exactly. So that's the constraint, is that you need either this condition to hold, so I comes from the first set and j is arbitrary, or j does. So this is just a slight subtlety here that if you think about the linear space over matrices, this is an n-squared dimensional vector space. So this vector space has n minus r squared. So, its dimension here is n minus r squared. That's the dimension of this vector space, because you're requiring both I and j to come from this augmentation. Now, the way that you define the orthogonal complement to T perp then, in order to define T, is that at least one of the two has to not come from the augmentation. So that's the way to define it. And this way, this really is, a vector space and its orthogonal complement, just over n-squared dimensional spaces. And it's easy to check that each of the generators that I've defined here really is orthonormal. This is an orthonormal set, and this is an orthonormal set. So we'll often be interested in this projections into these spaces, because what we really care about, the reason for working with something like T and T perp is that when we make progress towards getting the right matrix, well, maybe it makes sense to measure progress based on how close we're getting within this restricted subspace T. So that's the way that we'll actually use it. So just to make sure that we understand the definitions, let's say I want to project some matrix Z into the set T perp. So this you can define in the usual way. It's just the usual notion of a projection, because what we do in this case is we sum from r plus 1 to n, and over j equals r plus 1 to n of the inner product between z and ui vj transpose, all times ui vj transpose. So this makes sense, right? This is just the usual definition. I'm treating z as a vector because I'm really treating it as a vector of length n squared, and taking its inner product with this vector of length n squared, and then this is just the usual notion of projection. So the important thing is that we'll be looking at linear spaces over matrices, but they act in the usual ways. You just have to get comfortable with the fact that we're working over matrices and using the matrix inner product. So this expression, actually, you can rewrite it in a sort of more convenient way, because I claim that this thing is actually the same thing as z ui transpose times vj. So that's just the quadratic form of this pair of vectors on z. And now what I can do is I can take this, this is just a scalar value. So I can multiply it by ui and then times vj transpose, and just put the scalar value in between these two vectors, the outer product of these two vectors. So that's an equivalent way to write this expression. And now this actually gives us a rather nice way of thinking about this, because what I can do is I can just factorize it as So I can just factorize it as the product of these three matrices, just by rewriting this expression. Because I can just take the sum from I equals r plus 1 to n and collect these ui transposes. So all this is this is just the projection onto the span of the u's. So what you're doing when you project a matrix onto T perp is you're just projecting each of its columns to be in U perp, perpendicular to the first R UIs, and you're projecting its rows to be perpendicular to V1 through V1. So it's a very simple expression, right? So at the end of the day, what we end up getting is we just get that we're taking P U perp times Z times P V perp. And that's explicitly what this linear operation, this projection operation into T perp does. So that makes sense, right? So now, as a pop quiz, can anyone tell me what happens when I take a matrix and I project it into T? In fact, let me ask a very concrete question. If T perp, all we did was we just projected the columns into U perp, and we projected the rows into V perp, is it true that when we project into T, we just project into U, the rows, and you project the columns into U and the rows into V? Is that true? No? Okay, so someone who was shaking their head, tell me what it is. The answer was no. So the PU, Z, plus yes, perfect. So you have to use inclusion exclusion here. You can do it the same way if you think about explicitly, even though the projection in a linear spans over matrices looks a little bit counterintuitive, you can always go back to this definition. Because what I gave you was I gave you an orthonormal basis for the linear span over matrices. So you can always write it in this type of form, where the way to think about it is that what it is, PT of Z is just the sum over all ij, where you take all possible orthogonal vectors, matrices here, from this set, and you take its inner product and you add that vector, which in this case is a matrix because it's ui times vj transpose. So then the important thing is if I did the same trick of collecting together the ui's, well, I have this issue that I can collect together all the ui's from 1 to r and collect all the vj's so that I'm not doing anything here. And I can do the same thing where I can collect together all of the ui's from 1 to n, and I can collect the vj's where j ranges from 1 to r. But the issue is that then I've double counted the things which are in both, where both I is from 1 to r and j is from 1 to r, so you need to pull out this in order to do inclusion-exclusion. So the same way you can actually just explicitly manipulate this equality, which is just a literal translation of what it means to project a matrix into a linear span over matrices, and lo and behold, you figure out what the operation is. So all of this is just designed to get you comfortable with what it means to work with linear spaces over matrices. All of the usual things work because we're really just treating the vector, the matrices themselves as larger vectorized matrices. But there is the subtlety that, for example, when you define T perp, it has n minus r squared dimensions. So you can't just define T based on I and j are both in the range 1 to r. You need to make sure you cover all the remaining dimensions, which is what we're explicitly doing here. So this is the T and this is the T perp that we want to work with. And now I can tell you what this helper matrix Y is. So that's our goal, is the first thing is just to define the properties of this helper matrix Y. This mysterious thing which is going to let us prove that nuclear norm minimization recovers the true matrix. So I'm going to state the properties of Y, and then what we're going to work towards is we're just going to show that those properties really are enough to establish this, and then we'll worry about constructing Y. So I'm just taking a slightly roundabout way so that we don't spend all of our time just doing brutal, matrix turnoff bounds, but we try and see the big picture of how to actually realize this goal. Because it's actually a very similar goal to, the way that Feige-Killian and other sorts of SDP approaches work for showing that you get exact recovery. So now what we want with high probability over omega is we want that there is a matrix Y which has the following properties. First one's easy. Just going to allow Y to be supported in omega. Very simple property. The rest of the properties, you're not, the remaining two properties, B and C, you're not going to see quite yet why they're useful, because let me state them, and then we'll show why they're useful. So I want to show you why such a Y. This helper Y really does help us establish this goal, that nuclear norm minimization works and gets exact recovery. And you won't immediately see why these properties are the right thing. But the remaining thing is that we would love for y to be close to uv transpose, because it's going to act as sort of a dual certificate in some way for proving a lower bound on the nuclear norm. But y itself is going to be supported in omega, and omega is a very sparse set. So instead, what we're going to settle for is that we want pt of y to be close to uv transpose, which, if you remember, is what the perfect dual certificate is for what the nuclear norm of m is. So we want that this quantity is going to be small. And how small? I'll just tell you what the answer we're going to need is. And the last property we need is that we're going to need that y doesn't have too much mass off of t. So this condition says that when we project y, subject to our constraints that's supported in omega, onto t, we should get something close to the perfect dual certificate. And we want that y doesn't have too much remaining mass when you project it onto the orthogonal complement to that. And we'll just want that this is at most a half, the operator norm here. So this is over Frobenius norm, this is over operator norm. And these are the conditions we're going to want for y. So let's try and make sense out of this, right? This is a rather bizarre set of conditions. So let's think about why this is at all related to proving this goal. And let's realize this plan, subject to such a y existing. So we'll just take it on faith for now. So let's follow through on the plan that I gave you last time. So what we're going to do is remember that the only way that we can prove some sort of lower bound on the nuclear norm for m plus z is you give me the z, and I'm going to construct the dual certificate that proves that it has large nuclear norm. How large? Strictly larger than m's nuclear norm. So we remember what the dual certificate was to prove the nuclear norm of m star. That's just uv transpose. And what we want to do is we want to augment to that dual certificate. So the way that we're going to do this is we're going to take pt perp of z. So you give me z, and I hypothetically in my mind, let's say I already knew what t and t perp are. This is just a thought experiment where I can pretend I know everything about it. And what I do is I take z and I project it onto t perp. Right? And let its left and right singular vectors be u perp and v perp. I'll just name them that way. So let me tell you what the dual certificate we're going to use is. I can write it out explicitly. So we're going to take what was the perfect dual certificate for the nuclear norm of m, and because we have some extra freedom, because this is only R, rank R, and we can still define our dual certificate any way we want off of this space, what we're going to do is we're going to define it based on what z is. So we're just explicitly going to write out this b. So does this statement make sense? You give me the z, which I want to prove this inequality for. And remember that uv transpose, that is u sigma v transpose is the SVD of m. So what I'm going to do is then I'm going to take whatever z you give me, I'm going to project it onto the space which I still have freedom, which is t perp. And I'm going to take its singular vectors and add those to my set. So that's all that I'm doing. So the claim here is that the operator norm of B is indeed at most 1. Anyone know why this is? I mean, it's just a one-sentence statement. So actually, let's ask a more basic question. Why do I care what the operator norm of B is? So I want to take the inner product between n plus z and b. In a way that I prove a lower bound on the nuclear norm of n plus z. That's what I want at the end of the day. So I want to show that this nuclear norm is large. So why do I care about the operator norm of b?
Well, that's true, then so if the operator norm of B is at most 1, then that's automatic.
Exactly. Because remember, the dual characterization of the nuclear norm was that I'm allowed to take its maximum inner product over all matrices whose operator norm is at most 1. So if I don't have this claim, if the operator norm were larger, were really, really large, then the problem would be that this inner product, I'd like to use it to reason about the nuclear norm, but I can't, because it's not a valid lower bound. So I care about the operator norm of B because it gives me a dual certificate. Only if the operator norm of B is at most 1 is it a valid dual certificate. So that was the dual characterization of nuclear norm that we gave last time. So now with this in mind, why is the operator norm of B at most 1?
So then singular values and small values.
Yeah, I gave you the singularity composition right here, right? If I ignored this part, it's just flat out true because the columns of U are all orthonormal, the columns of V are all orthonormal. But now the important thing is this is exactly why I defined T perp the way that I did, is that you can only use columns and rows from the augmented set. So the first column of U perp is indeed perpendicular to all the columns of U, and the first column of V perp is perpendicular to all the columns of V. That's the way I've constructed it, is I've constructed this space T perp in a way that it's true. That if you remember what the definition of projecting onto T perp is, I've made all the columns orthogonal to U and all the rows orthogonal to V. So in this way, I've explicitly enforced the fact that when I take Z and I project it onto T perp and take its singular value decomposition, those vectors are themselves perpendicular to all of the things I've found so far. And it's just a valid way to extend the SVD without increasing the operator norm. So the proof is, we explicitly gave its SVD. And that's it. Okay?
So basically that's equal to U and U transposed next to each other in V.
U and V, yeah. So it's, I can think about it this way, is this is an n by r matrix. This is some n by n minus r matrix, at most. And the same way, I have to worry about the transposes from the dimensions, but the same thing is true, that I'm really just augmenting to U. So you can think about it two different ways. You can think about it as, block matrices, or I can explicitly multiply them out in this way and get this expression. So these are all different ways of thinking about what B is. But from the way I've constructed B, I've explicitly enforced the fact that it's a dual certificate. So I want you guys to understand the plan. If we go slower, that's fine. Worst case, we cut alternating minimization from the next lecture. Not a big deal. That'll be your third P set if we do that. I'm kidding. All right, so the important thing is, let's see now. Now we've got our plan of action, right? I want to prove the nuclear norm of n plus z is strictly larger than the nuclear norm of n, and B is the way I'm going to go about doing it. So let's try using B and see what happens. And then we'll see how this plan actually makes sense, right? So let's do that. So what I have so far is I have m plus z star is at least the inner product between m plus z and b. And this is true because this is the dual characterization of the nuclear norm, is that I have a b, which I've explicitly written out there, whose operating norm is at most 1. So its inner product, is always a lower bound for what this nuclear norm is. Right? That was the dual characterization we talked about last time. Now let's write this out just to be a bit more explicit. So this is m plus c, inner product with uv transpose plus u perp v perp transpose. Now what if I take m and take its inner product with uv transpose and take m's inner product with u perp v perp? So what if I just write this out instead as m inner product uv transpose plus u perp v perp transpose? Oops. So there's one term I can remove from here. What can I ignore?
And the product of n with the second.
Yes. That's 0, right? Because each of the columns here is orthogonal to all of the columns in M. And in fact, it's even true because all of the rows in V perp transpose are orthogonal to all the rows of M. We've really made this term 0. It's 0 in 2 different ways, right? What about this remaining term? What is this?
Nuclear norm of M.
Yes. This is the nuclear norm of M. That's good. Right? So at the end of the day, all we need to prove is that this term is strictly larger than 0. And then we'll have the statement that we're after, right? See, we've constructed the dual certificate in a way that its remaining part doesn't interfere, so we took something that was the dual certificate for M's nuclear norm. And we augmented it in a way that it didn't affect what we get against M with the inner product. And that's the sense in which we haven't destroyed the part we wanted to get to begin with. But now we just need to know, see, this U perp V perp transpose was designed to give me some sort of nuclear norm related to Z. I just want that I haven't swamped it by the other term that I want to ignore. So let's think about what this means. So I claim that at the end of the day, all we want is we want to prove that the inner product between Z and UV transpose plus U perp V perp transpose is strictly larger than 0. And that would imply exactly what we're after, that nuclear norm minimization exactly recovers N. That would be the completed argument, right? So how do we go about proving this? Why should this be greater than 0? Even intuitively, forgetting the calculations, this only comes from massaging this term in a way that we can pull out which is the term that's going to be large and which is the term which is small and negative and hopefully gets swamped by the other term. So one way of thinking about this now is what we can do is I claim, and you guys should tell me why, is that this is the same thing as PT of Z, PT of UV transpose plus U perp V perp transpose plus PT perp of Z PT perp of UV transpose plus U perp V perp transpose. Why is that true?
We can just forget the matrices and just distribute it.
Yeah, exactly. Right? So I mean, I want to make sure, the first time you see these, linear space over matrices, it looks a little unfamiliar. But this is really just the standard linear algebraic fact, right? Because forget that these are matrices. You're really just taking their inner product as if they were vectors. And I'm just saying that their inner product is the same thing as projecting into two, orthogonal spaces that fill up the entire space. You take their inner product in one, and you add that to their inner product in the other. It's the same thing as why orthonormal transformations don't change the inner product. But now I can remove some terms. So can anyone tell me some terms I can remove? Let me do one change to make the algebra a little bit simpler. Okay, forget this part for right now. We're going to come back to it 1 second. One thing I claim is that these two inner products are equal. Anyone tell me why that fact's true?
Z is supported in the complement operator.
Sorry, what?
Z is supported in the complement operator.
Yep. And y supported in omega, right? So the inner product between z and omega is 0 because they're supported in disjoint sets. So I can add and subtract y freely. That's why y is a helper matrix. Now what I'm actually going to do is then I'm going to put in minus y. And minus y. That's the same reason as I had this inner product between z and this set of matrices, and I take it over, when I do PT, and I take it when I do PT perp. But now something should get simplified, so can anyone tell me a term I can cross off? I don't like this many terms. Yes, this is 0. PT just kills it. Anything else?
Also, the first
Yes. All right, good.
Did we need y for that?
Huh?
Did we need y? Yeah, no, right?
Nope.
Okay.
We're going to exploit y in a minute. So there's a reason why I sort of put it in earlier is because now we're going to try and exploit it. So let me just save myself a little bit of space and kill this line. And now all of this at the end of the day is equal to, just to write it out, PT of Z, so inner product with UV transpose minus PT of Y plus PT perp of Z's, inner product with U perp V perp transpose. Sorry, PT. So now we're actually starting to make progress. So what is this inner product between these two terms?
nuclear normal for PT per Z.
Yes, exactly. So let me just write it out this way. But Do you guys see why that is? That's the way I've constructed this certificate, is I took Z and I projected it onto T perp, and that's exactly how I got U perp and V perp transpose, where they were its singular vectors, and its singular vectors realize as a dual certificate its nuclear norm. Right? So, yeah, let me, I guess, just write it out this way. Is this is the nuclear norm of PT perp of Z. Right? And the other thing I claim is that how large can PT perp Z's interproduct with PT perp of Y be? And the hint is to use one of the three properties of Y.
That's a half of the nuclear norm.
Yeah, can be at most half of the nuclear norm, because the operator norm of PT perp of Y is at most a half. Right? So all of this at the end of the day tells us that this entire part right here is at least a half of PT perp Z star. So this is the part that we want to show something is strictly greater than 0. This is the part we're winning, just based on the way we've constructed U perp and V perp, and the fact that Y has very little mass on PT perp. And this term, we're going to try and exploit property B now, right? Because we know that the Frobenius norm between these guys is small. So it can't contribute something too negative from the other side. So this was the part where we were designing it to pick up something of this, you added Z, and I look at your Z, and I construct this B in a way that I'm trying to pick up some of Z's mass and make this inequality strict. I win some, and I lose some, and I just want to show I win more than I lose. So it's actually very similar to the types of arguments you use in compressed sensing, where you take a particular planted solution and you hypothesize there's some other L1 minimizer, but lo and behold, the vector in the kernel has to add more than it can subtract off. That's a sense in which any hypothesized change Z has to add more to the nuclear norm and contribute more than it can possibly subtract off, is that I should win more than I lose. But this is much more complicated here, because in the sparse recovery setting, well, that was actually just a true statement that any vector in the kernel is spread out enough that it just can't subtract as much as it adds. But here, the way that I'm proving that's true for a Z is I have to design my dual certificate based on knowing what Z is. So there's this extra layer of indirection, which is what makes matrix completion interesting and more challenging than the sparse recovery setting. So you can see from this that many of the same intuitions we gave for sparse recovery are still playing out here. There's this complication that we're dealing with linear spaces over matrices, but the main complication is that we really need to construct this matrix B based on knowledge of what Z you've used. And that's really the biggest difference until we get the quantum golf. So at the end of the day, what I claim that we get for this inequality is that this is, well, we get this nice term that we benefited from, PT perp of Z star, a half times that. And how much we could possibly be subtracting off, I claim, is at most this. So this inner product right here, just treat this as a vector. Its Frobenius norm is just the 2 norm of that vector. And we know that it's at most r over square root of r over 8n by property B. And we take its inner product with this guy, and we take its Frobenius norm, and that's how small this inner product can be. That's how much we lose. So it turns out that you can prove that with high probability, this is greater than 0 for all z's supported in omega. It's really just a property of all z's supported in omega that they have to have a large component in T perp compared to what their Frobenius norm is scaled by this tiny factor. We're going to prove that later. This is really a matrix concentration bound. That's the same way that we're going to construct Y, so I'm really going to table this inequality. I can state it precisely, but the lemma which we're going to defer the proof of is that with high probability, for all Z supported in omega complement, that the nuclear norm of PT perp of Z star is strictly larger than 2 times R over 8n times PT of Z for Frobenius.
Is that 2 times or square root?
Sorry, what?
Is that 2 times the square root?
Yeah, 2 times. These constants actually aren't going to matter because we're going to prove that this is really, really true via matrix turnout bound, so I wouldn't worry too much about it. This is an inequality which I'm going to table for the time being because it really fits into how we're going to construct Y. But this is part 1 of today, and I want to make sure you guys all understand this. Part 1 is why this helper matrix Y actually proves that nuclear norm minimization gets the exactly right answer. And that's what we just did, modulo this one inequality. So that's part 1, is why does Y help? Why is it a helper matrix? And this is a lot of the intuition about how you're going to prove a statement like M plus Z star is strictly larger than M star. Is you do it through some helper matrix, which that helper matrix, and the certificate you're using is really dependent on what Z is. So that's really a property of matrix completion, which is important. The remaining part is now we can actually get to what quantum golfing is and what matrix turnoff bounds are. So I'm going to prove this statement, and I'm going to prove that Y exists. And we're going to do it through concentration bounds for sums of independent matrices. That's the way we're going to go about doing it. But this is the main part of today. Are there any questions about this? Yeah?
So far we haven't used the properties of omega and the coherence.
Exactly. That's a very important point, is that the way I've separated out the parts of this proof is it's always important, and it's not always done when you write these things, when you see the writings of these things, is that it's great to separate out what are deterministic properties and what is the part that you're going to use the stochastic properties to actually construct those things you need. So the same way it was true in sort of phi Gauquelian that we wanted to prove the SDP achieved exact recovery. Well, we needed that some particular, if some dual certificate had some PSTness condition and it was valid, lo and behold, it implied the true solution was optimal. That's a purely deterministic statement, but the fact that that was a valid dual certificate is the part where you're exploiting the randomness. So I think when giving an exposition of these things, it always makes sense to separate out what are the deterministic statements, which are all conditional statements. If these things are true, then nuclear norm minimization works, compared to the things which rely on the random properties, which show that those conditional statements do hold with high probability. So it's a great mental thought exercise to do when you're reading other things in this literature. For example, it's definitely true in smooth analysis that smooth analysis you think of like perturbing your instance and making it easier for an algorithm. But what's always true is that you're saying a perturbation moves you into some easy space of instances, and it helps a lot to try and explicitly identify what that easy space is. That's a separate thing about understanding properties that make algorithms work than showing that that property holds with high probability in a smooth model. So I think it's a very useful thought exercise, but thanks for that question. Any other questions about this? You can slow me down if I'm going too fast. All right, let's prove y exists now. Okay, for the sake of brevity, what I'm going to do is I'm going to tell you a powerful tool called the matrix Bernstein bound. That's the main workhorse between proving this lemma and proving that y exists with high probability. That's how you actually prove this lemma. But I want to do is I want to emphasize what this tool is and tell you what quantum engulfing is, like how that tool fits in to how you should try and construct such a y, because this y looks rather mysterious. It looks like something we pulled out of thin air, but there's a really nice intuition once you understand, once you understand matrix Bernstein about why such a y should exist. The rest of it is sort of dotting i's and crossing t's and doing some rather painful calculations. So if we have time, I can do those. But right now, I want to tell you what the matrix Bernstein bound is and what quantum engulfing is, where the matrix Bernstein fits in. So what's a really important tool, and let me just state it, is that the same way that all of you are probably familiar with concentration bound for sums of independent random variables, well, there are also nice concentration statements that hold even in non-commutative settings, where you're thinking about sums of independent random matrices. That's exactly what's going on here, because when we take observations of our matrix, we can think about it as a sum of independent random matrices, which we understand what its expectation looks like. So, let me state this theorem. This was proven by Allsweet and Winter, the first version of this. A really beautiful result. It's not obvious the first time you see these things. So let x1 through xl be independent, random matrices. They don't even need to be identically distributed, although in our setting they will be, of size n by n. You can also do it in the asymmetric case, nothing really changes. Let's keep our notation as simple as possible. So, moreover, we're going to have the property that the expectation of xk is the all zero matrix, and that every xk, every realization of it, has operator norm at most some n. So this is the same way that when n equals 1, I take the sum of mean 0, random variables who have some bound on how large they can ever be. The other thing that we need for typical concentration bounds is we need some notion of the variance in order to understand what the variance of the overall aggregate random variable is. Now there's a subtlety here which is quite interesting, is that there are two ways that you could think about defining the variance. And you need both of them to be bounded. Because one way of defining the variance is I could take the expectation of xk transpose, the operator norm of this. So in the case where n equals 1, and these are sums of scalar random variables, all this quantity is the variance. But there's another way to write the variance, which is I could instead write it as the expectation of xk transpose xk. These xk's are not necessarily symmetric matrices, so these are not necessarily the same quantity. That definitely shows up when you talk about an n1 by n2 matrix, and you have no hope that these two are the same thing, because they would have different dimensions to begin with. Well, you define the variance as actually the max of these two. In the scalar setting, you have no complication, because these would be the same quantity. Then the matrix turnoff bound, it just tells you that for all tau greater than 0, the probability that the sum of k equals 1 to L of xk, so this is a matrix that its operator norm is larger than tau, as at most 2n times e to the minus tau squared over 2 summation rho k squared plus m tau over 3. So let's sum that. Which, in the setting where these are scalars, you can see that it recovers the standard Bernstein inequality, if you know what that is. But the important consequence of all of this is that what you're really saying is that with high probability, you have the property that the operator norm of sum of xk from k equals 1 to L, well, it behaves roughly like c times the max of square root summation k rho k squared log n and m times log n. So if you plug in some tau, which is equal to this max, this is the setting that we'll really care more about. As you plug in this tau, and in our setting, this term is not going to dominate. So you're going to end up with the square of that. So you get the summation rho k squared times log n. The rho k squareds cancel, and you get this log n, and you get with high probability that your bound is true. So it's like this should exactly remind you of the scalar case. Because you add up the variances, you multiply by log n, you take the square root, and that's what you would expect when you add up, for example, independent Gaussian random variables, is you would get that type of concentration bound. The miraculous thing is that this also holds in the matrix set. And this is actually a very deep statement that it holds in the matrix set. So it's really not obvious the first time you see it. Does the statement make sense? Any questions about it? I'm not going to tell you how to prove it either. That's a whole other can of worms. It's a deep statement.
Is it much more complicated to prove than in one dimension?
No. So how can it be deep and not more difficult? Is you need some inequality about the exponential traces versus the trace of exponential matrices. And then the right proof of the one-dimensional thing, plus something called the Golden-Thompson inequality, yields this. But it's a very surprising thing, and inequalities like the Golden-Thompson, the same way, people often get those things wrong and get the inequalities in the wrong direction. It's the same way that, like, the trace of, ACB, you don't get all the permutations of it. It's another very common mistake, although a higher tech mistake, but a lot of times people make that mistake. So it was proved by Allsweet and Winter, not actually that long ago in quantum settings to try and analyze the quantum capacity of channels, but I don't know much more beyond that. So let's think about what this means. So let's see. So there's actually going to be a key lemma that we're going to use to prove y exists and to think about what quantum golfing means. So let me tell you a lemma, which is going to connect to this theorem. So I might or might not prove this lemma, but this is the lemma that I want you to understand. And you should think about it as being really a consequence of something like the matrix Bernstein inequality. They're also the same way that, there's like all these concentration bounds for scalar random variables. There's Bernstein, there's Hinching, there's Chernoff. There are matrix versions of all of them. So a lot of these things really do work out nicely. And the first time you see it, it should actually surprise you if you haven't seen it before. So let me tell you the key lemma we're going to use in order to figure out why such a y should exist. And let me just define it. So I'm going to let some other operator, so we have this PT operator right now. There's a very simple operator that we'll need just to get the ball rolling, is it's just the one that takes a matrix and masks the unobserved entries. So does this operator make sense? All you're doing is you're keeping in all of the entries you observe. You observe Zij, and you put that entry in the ij entry in some matrix. And nothing else contributes. So it's a very simple operator. Now the other thing is that actually we're going to need one further layer of indirection here, which is not actually a layer of indirection if you think about it, but since we care about operators, let's consider some arbitrary operator. We have things like PT and R omega. We're going to consider combinations of them. Let's say we have an operator that goes from n by n matrices to n by n matrices. That's what all of our operators do. PT does that, PT perp does that, R omega does that. Well, what we'll care about is we'll care about the operator norm of the operator, which all it is it's the max over all z's, whose Frobenius norm is at most 1, of the operator applied to z's Frobenius norm. So if you think about z as itself being a vector, even though it's a matrix, then all this is P is a linear operator, or is an arbitrary operator. For us, will be linear. Then all you're doing is you're looking at the standard operator norm. Because the natural 2 norm of this matrix is its Frobenius norm. That's the sum of the squared entries, square root of the entire thing. And we look at how much it can increase this. So this is just, when we have these operators, we can care about how much they can increase the Frobenius norm of a matrix. So we'll care about something like this. Now let me tell you the main lemma that we need to prove all these things. It's used in why y exists, and it's used in the proof of this. And at first glance, it's not going to look like matrix Bernstein, but it is. So let me state it. Then what we'll say is that if the number of observations is at least nr log n, then with high probability, if we take this operator pt r omega pt minus m over n squared pt, this is some operator. And it has some norm associated with that operator in the same way that we have this definition. I want to say that with high probability, this thing is less than a half. So this is a statement that holds with high probability over omega. So does the statement itself make sense? You shouldn't yet see why it's true or even why it fits into matrix Bernstein. But everyone gets the statement? I'm just saying this is some random operator. Random because omega is random. And I create this operator based on omega. And I want to say that with high probability, it acts like this. So why does, yep.
What is M here?
M is the number of observations. Let's say you plug in M is n squared, and you observe the entire matrix. Then this is just the identity. PT times the identity times PT is PT. This is 1 times PT, so you get 0 for this operator norm, so that's a good starting point. The other way to think about it is that the expectation of this operator is that. Right? So the claim is that the expectation over omega of this operator PT R omega PT, well, PT is not random. Only R omega is random. And these are all linear operators. So you can just think about it as PT times the expectation of omega of R omega times PT. And this guy right here is nothing more than m over n squared times the identity. Because each entry has that probability of being observed. As we choose m random entries, so it's m over n squared. So lo and behold, we get m over n squared times pt. So this is really a question about why some random operator is close in the norm of it as an operator to what its expectation is. And there's actually a way to think about this as a sum of independent random matrices. So let me explain how you should interpret this statement. And we're going to not fully prove it, it's just a matter of using this matrix Chernoff bound. But let me just interpret what that lemma means. So let me give you the proof sketch. Okay? So let's think about what this operator, pt of z, is. First thing I want to do is I want to give you a more convenient representation of pt. Then we're going to use that to give a more convenient representation of pt r omega pt. So what I claim is we can just write this out explicitly as it's the sum over all ij of the inner product between pt of z and ei ej transpose times ei ej transpose. It's kind of a vacuous way to write this out, right? A matrix is just the sum of its entries in each location. It's a really silly way to write it out. But what I can do that's kind of nice here is I can now write this out as sum over ij of the inner product between z and pt, ei ej transpose times ei ej transpose. You just move the pt operation. These are really just vectors, right? The inner product between two vectors, when I take this vector and project it onto some space and take its inner product with something else, I could have just projected the other vector. Also, that doesn't change their inner product. And then I can just remove this projection. That preserves it. So I can shift this pt operation. Does that make sense? That's something I can do. I tell you why I want to do it yet. Okay. Now I claim r omega pt of z as a kind of nice expression. It's sum over all ij in omega of z pt of ei ej transpose times ei ej transpose. And now finally, what about pt r omega pt of z? Can anyone tell me what that expression should be? Just making sure you guys are awake. It's too easy?
It's the same as the proof.
Not quite. I need to change one thing. I mean, this is a scalar, but I still need to apply pt here. So what this really gives me is it gives me sum over all ij in omega of the inner product between z and pt ei ej transpose times pt of ei ej transpose. So that's my convenient expression. Because you can think about this now, this operator is the sum of independently chosen operators. For any ij I observe, this is some operator. This inner product here, we take the inner product with z times this, and we multiply it by this guy. And that's an operator. I can call this operator tau ij. And what I have is that my operator is the sum of independent operators. But you can really think about these operators as really just operating on vectors. If you vectorize the entire thing, Z is some vector, vectorized matrix, and it's taking its inner product with this vector times this vector. So this is really nothing more than the sum of independent random matrices, where the matrices look like this vector outer product with itself. That's actually what allows you to prove the concentration types of bounds, like this type of lemma will be true as a result. So you can work out what actually the matrix Bernstein tells you in this case. And what you need to estimate are things like what the variance of this random operator is, which then involve things like the incoherence and the rank, and then lo and behold, you get those statements. Let me just take it for granted because the rest of it is just a few calculations. And let me actually tell you what quantum golfing is now that we have this idea. So this idea, this is the key lemma. It's just an operator norm bound for a random operator. And that itself may look strange, but it's no different than the sum of independent random matrix, matrix valued random variables. So without further ado, let's do quantum golfing. Let me keep up the properties there. Keep this up for the time being. So I hope to finally tell you why it's called quantum golfing. So remember, now our goal is to try and use these tools. We have this lemma, which came from the matrix Bernstein down, and we want to construct such a Y. So what we're going to do is we're going to take omega, which is our set of observations, and we're going to break it up into omega 1, omega 2, up to omega p, where p equals c log n. So we're going to have log n swings in this golfing thing. Each omega is going to make progress towards constructing the line, and we want to show that we make geometric progress. So even just for one of them, so let me tell you how we're going to define y. There's a very simple algorithm for constructing y. Now this is just a hypothetical algorithm because it uses things we don't know. It uses what u and v are and other sorts of things. But what we're going to do, let me define it first. We set y0 to be 0. There's nothing we can do when we don't have any observations. And then, lo and behold, our remainder, we're trying to get close to uv transpose. Our remainder is just the entire thing. We want property b to be true. And our remainder we'll keep track of as w0. Now, y1, what we're going to do is we're going to set it equal to y0 plus n squared over m r omega 1 of w0. So we take this hypothetical matrix we'd like to get. Now we're restricted to constructing y so that it's supported in omega. And we're going to do it piecewise because our first attempt is just going to use the entries in omega 1 to make progress. And how's it going to do that? It's just going to take w0, our current remainder, and restrict it to the set of things which we've added to our current set of observations, scaled by something. We're going to add it back in what our old thing is, but in this case it's 0. So the next thing that we should do is we should update what our remainder is. Well, our remainder is just uv transpose minus whatever we've gotten so far. y1 is our current guess. So lo and behold, we take y1, we take its pt, and we look at uv transpose minus that. That's our new remainder, because that's what would be the entry in this b term right here. is we're just taking pty minus uv transpose. So what do we do now? Well, we set y2 to be equal to our old estimate, but we add in things from our new estimate. Except we use omega 2 now, and we use our current remainder, W1. And then we update our remainder. It's just UV transpose minus PT of Y2. So this is what's golfing about it, right? Is that we want to recover UV transpose. We want to get close to that when we want to have a Y whose PT is close to that. And we do it incrementally. We keep track of what the remainder is. And wherever that remainder is, that's the direction we want to hit towards the hole. And we use this randomness to hit in that direction. That's how we update our estimate. And then we have to update our residual. So we're just going back and forth. We're updating the direction we want to hit in, and we hit. And why is it quantum? Because we care about matrices. So that's kind of a letdown that there's no good reason for that nomenclature other than sometimes people call matrix things quantum because they're matrices. I don't know. So let me just write out what the full recurrence is, just so that we have it. So we have yi equals, yi plus 1 equals yi plus n squared over m r omega I plus 1 times wi. That's where we hit towards our new remainder. And then we update our direction quantumly because it's a matrix. Okay? So that's the sequence of steps we do, and I've written out what they look like. Now there are a few simple things. So first of all, the first claim is just that y is supported on omega. Why is that?
At each step we only add a
Yeah, by construction, right? See, y0 is supported on nothing. y1 is just getting its entries on omega 1. y2 is getting its entries from y1 and also from omega 2. So at the end of the day, our aggregate y is going to be the sum of all of these y. Is the last y we get out. It's just supported on the union of the omega i's. So that's a good starting point. So this proof is immediate. And now here's the main computation. So we have our quantum golfing strategy, but we don't know we're any good at golfing yet. So why do we actually make progress? So let's think about what progress means. Let's look at PT of yi plus 1 minus UV transpose. It's Frobenius. That's property B. That's the hard one to get right because we want it to be inverse column. The other thing, we just don't want too much of its mass to go outside of that. We've already satisfied property A. So I'll explain why C happens too, but B is really the heart of the matter. So we care about this guy. And now let me just write out what yi plus 1 is. So we can write this out as just PT of yi minus UV transpose. So I've taken the UV transpose, and now I need to take the n squared over m PT r omega I plus 1 of wi. It's Frobenius norm. So that's just explicitly plugging in what yi is. I add these two terms based on expanding yi plus 1, and then I'm subtracting off this term. Now this is a good starting point because this quantity right here is Wi, by definition, right? And let's see. What I claim though is that by construction, so this will be the other claim that I'll need, is that by construction, PT of Wi equals Wi for all I. Right? Think about applying PT to Wi plus 1. You keep this term, and this is already PT'd, so you haven't done anything. So this is good, because what this means now is that this entire quantity is equal to sorry, this should be minus Wi, so this is minus PT of Wi and plus n squared over m PT r omega I plus 1 PT of Wi. Right? It's just writing this out. So at the end of the day, all of this is now equal to n squared over m times PT r omega I plus 1 PT of Wi minus m over n squared PT Wi for bins. I've just pulled out the n squared over n. And now this should look pretty familiar. I guess let me put this down to MD. That's our lemma. That's why golfing makes progress. This right here is rather minus Wi plus 1. So it's really this entire quantity. Gives us the Frobenius norm. And it's decreasing geometrically. As soon as each omega I is at least n times r times log n. At the end of the day, we do that log n times, so we get n times r times log squared n. And then we can drive this error down to whatever we want it to be. It doesn't actually matter, we had this property b that we cared about. So we definitely satisfied k just by construction. We satisfied b because we're just driving this error down to something really, really tiny. And the intuition for c is that if you think about, y, it's the sum, it's like, it's the sum of these increments of, you go from y0, and then you add something to get y1, you add something to get y2, and so on. And really the important thing is that PT perp of y0 is small, is let's say a quarter, and geometrically, W is decreasing so fast that your increments are decreasing geometrically too. So it's really the first term that dominates your contribution. And that's actually how you prove C. And I guess I won't get into this thing also implies this missing lemma in here. It's a little bit messy to compute this. If you want to take a look at it, it's all in the notes. So this lemma actually implies this, and it's a kind of ugly bound. But they all follow from this. And the important thing is to understand why quantum golfing works. You're using the matrix Bernstein to make progress towards the thing that you want to represent. You want to represent UV transpose with some y so that PT of y is closed. And each time, y is supported in omega, you're adding some new set to omega, and you're making progress in the direction you'd like to go. And that progress, your error is decreasing geometrically so that you really do get close to this, all the while you're not stacking up too much error on the orthogonal complement. So this is matrix completion. It's a little bit harder than sparse recovery things, but it's really interesting how the same ideas get used in place there. You know, about showing that the SDP gets exact recovery. There is this extra nuance in there. You know, the two important things to take away are that the way that you prove you get the optimal, true answer is with a dual certificate that depends on the thing I want to rule out. You give me Z, and I gave you a way to construct the B that proves n plus Z star is strictly larger than m star. So that's the important point one. Important point two is that a lot of times you pass to the dual, the same way we did for Feige-Killian, and you think about what type of certificate would exist in order to show that, that thing that those deterministic conditions you need and hold, this helper matrix Y. And that's where you're really using the stochastic properties of the model. You can use the stochastic properties, and you can also use properties of the thing you're recovering. I don't know what T is, and I can't even carry out this procedure if you gave me the omegas, because it's really starting with what UV transpose is. That's what I want to learn in the first place. But in the dual, you can just pretend you know everything, and in that way use the matrix turnoff bound to make progress. So that's it. So we'll do, I guess, alternating minimization next time. And then we'll do an Ask Me Anything on the last day. So, your turn to flip the books. Anything's fair game. All right. Yeah, so I hope to grade them on my way to work this weekend, and then I'll have them. Oh, no, not yet.
And could we have solutions at some point? Or office hours to ask questions about
Office
them?
hours to ask questions you can always have.
But I need the piece set back, I guess, for that.
That we can do.
Yes.
Yes. Yeah, yeah. You're